All right, welcome back. As you can tell, I'm not here, so you get to listen to my disembodied voice and my disembodied hands. You get to watch them do some stuff. So this is the last lesson of the unit. And last time we talked about something called covalent bonding, which is where you have an atom like chlorine, for example, which has 7 valence electrons by itself. We know that this is not the most stable state that chlorine can be in. Chlorine wants to have a full valence shell of electrons, wants all 8 valence electrons that it could have, because it's going to be in that third row on the periodic table, and we know that periodic trend. Now, it's not going to be able to do that by itself, and it's not just going to suck in an electron from anywhere. What it's going to do is, if let's say another chlorine is nearby, what will happen is separately, these two chlorines will have 7 valence electrons, but when they connect to each other and they share that one valence electron with each other, you can now see that this chlorine right here in my left hand has 8 valence electrons around it, and this chlorine in my right hand also has 8 valence electrons. And that's what we call a covalent bond, right? It's when two atoms combine together because their valence electrons are shared. What I'm going to show you today is a different type of bond called an ionic bond, where you might get something like sodium, which has 1 valence electron, and chlorine, which has 7 valence electrons, and they also will connect. But as you can see, there's a difference, and we're going to talk about what that difference is. And you may already see it for yourself, but let's go ahead and jump right in. All right, so what we understand is that covalent bonds, valence electrons are shared. This we already know, right? Covalent bonds, electrons are shared. In ionic bonds, though, valence electrons are actually stolen. And if we take a look at this model again, right, this one, which if you want to do this, you can pause your video right now. They're at the front of the room, and you can grab these. So do it quickly if you're going to do that. So regardless of whether you grabbed it or not, what you'll notice is chlorine wants that 1 extra valence electron, right? Sodium has the valence electron. And so chlorine is like, cool, awesome. Thank you for that valence electron. This chlorine now has 8 total valence electrons around it. But here's the issue. Sodium gave its electron to chlorine, but chlorine is not giving its electron to sodium. So in this scenario, chlorine has 8 valence electrons, and what it looks like is that sodium actually lost the only valence electron that it had. So the question is, well, how does that help sodium? Why would this work? And in order to understand that, we actually need to take a look at the periodic table really quickly. So what we're looking at here is the periodic table, and we can see the 2 atoms we just used, right? Chlorine's over here. Oops, that is not chlorine. Chlorine's over here, and sodium's way over there. Now, if we look, this is the tricky part, and maybe you can see it already. Chlorine needs to gain that 1 valence electron, right? And what it's going to do is it's going to gain a valence electron. It's going to get its full set of 8. In this situation, though, sodium, as we saw, lost its valence electron to chlorine. But what happens if you lose an electron in your sodium, right? You lose that 1 electron, you actually end up back over here. You lose that 3rd shell electron, but remember, sodium had all 8 of those electrons already in the 2nd shell, and so now it's left with these 8, and it has a full valence shell. So it's a little bit different, and yet the rules are still the same. So for sodium chloride, which is what we call that compound, which is really just table salt, in this case, atoms are connected because chlorine is going to steal a valence electron, I'm just going to abbreviate that, from sodium. And this is what we call an ionic bond. Now, when that happens, when atoms lose or gain an electron, we know that that's called an ion. So when atoms become ions, what's going to happen is they will end up being electromagnetically attracted to each other. And you may be asking yourself, Mr. Markowitz, how is that possible? If you take a look, This is our sodium, this is our chlorine. Sodium is going to transfer its electron to chlorine, but in this situation, sodium is now down an electron. It lost one. So now the protons in sodium, there's actually one more proton than electrons, and it's going to become a +1 ion. Likewise, chlorine, which originally has, it has 17 protons, a neutral atom of chlorine will have 17 electrons. It's now gained an 18th electron. So it has 17 protons, but 18 electrons. That means that it's going to have a -1 charge and become a negative ion. And what happens with opposite charges? We know this. Opposite charges will attract, and they will connect to each other. And that is how ionic bonds work. One atom is going to transfer an electron to the other. In doing so, each becomes charged, becomes an ion, and because they're oppositely charged, they will connect to each other. Now, here's the way that we can figure this out. How do we know if an electron is going to be shared or stolen? This is a trend called electronegativity, and that's going to help us. Electronegativity is a measure of how strong an atom is going to attract electrons to itself. And the periodic trend is that this increases, for the most part, diagonally up and to the right. And you can actually see an electronegativity chart down here, which I'm going to reference a little bit more in a moment. But you can see, and you might remember this from when we talked about it because I used a weird analogy, and I'm going to use it again, that if we're talking about the attractiveness of atoms, we know that francium and cesium, they're like super oogle. Like, they are not super sexy. They have terrible personalities. They have to buy their friends. They're just not very popular, and electrons are not very attracted to them. On the other hand, you have atoms like fluorine, chlorine, oxygen, bromine. They're super sexy. Electrons love them. They want to be near them. They don't even have to try, right? It's effortless. They just attract electrons super strongly. And what's going to happen is we can actually determine if an ionic bond is going to form based on the difference in their electronegativities. I'm never going to ask you to calculate it, but actually it's really easy to represent on the table, and I'll show you in a moment. But here's the rules. The lesser the difference between atoms' electronegativities, the more likely it is that they are going to share electrons. For example, if we take a look at a molecule like CO2, I'm going to write that off to the side, so this is a little example. Carbon dioxide. Carbon dioxide contains the atoms carbon and oxygen. And if we look at their location on the periodic table, they're very close to each other. Very close. Now, you could do the math. In general, electronegativities that are, and this should actually read greater than, if the electronegativities are less than 1.8, if the difference is, the bond's going to be covalent. But we don't really need to do that because we can see how close they are. They're very, very close to each other, and this is going to form a covalent bond where they're going to share their electrons because their electronegativities aren't very different. On the other hand, the greater the difference between atoms' electronegativities, the more likely it is that the more electronegative atom will steal an electron. So how does that work? Let's go back to our previous example of sodium chloride. All right, so this is going to be made up of a sodium and a chlorine atom. And if we look at their locations, sodium is way over here on the very unsexy side, and chlorine is way on the other side of the table on the super sexy side. They are very different electronegativities. Sodium has a very low electronegativity. Chlorine has a very high electronegativity. And because they are so different, Chlorine, being the more electronegative atom, will steal an electron from sodium, which has a much lower electronegativity. Now, what does all of this have to do with what I'm going to be assessing you on? Ultimately, I'm going to give you a chart that looks like this, all right? And I'll zoom in on it a little bit. It's going to look exactly like that, and I'm going to ask you a question that's going to be pretty clear. I'm not going to ask you about weird atoms that are in here. I might say, hey, all right, you've got a fluorine atom and a magnesium atom. What kind of bond is that going to form, and how do you know based on their electronegativities? And the answer to that one, if you want to do it yourself, pause and then check yourself. The answer to that one is this would be ionic, because fluorine has a very high electronegativity, magnesium has a very low electronegativity, and because they're so different, they're going to form an ionic bond. And fluorine will steal an electron from magnesium, okay? Now, another example might be, what if I gave you an atom like NO3, which is actually an ion that's called ammonia? What would happen in this case? Well, would this be covalent or ionic based on their electronegativities? Take a look at where nitrogen and oxygen are. So nitrogen and oxygen, they're right next to each other. They're really, really close in electronegativities. So what kind of bond would that create? It's going to make a covalent bond because they are very close in electronegativity. And those are the kinds of questions I'm going to ask. I'm never going to ask you about like weird atoms in here. It's going to be like where you're going to actually have to do the math with these actual numbers. It's going to be really obvious to you. You just need to be able to look, and you need to be able to explain, hey, fluorine is really far away from magnesium in terms of their electronegativities. That means they're really different, which means it'll be ionic, for example. And that's the end. We're going to do a little bit more in the lab where you're going to learn about how ionic compounds come together by charge like this, and how we can predict how many, like this positive ion, for example, how we know that only one of these is going to bond to only one chlorine based on their charge. And that's going to be the purpose of the lab. So let's get to it.